we've got a meeting.
Yeah, self-inductance in a circuit. Let's just have a quick look at this. Just make sure you've got it sorted. This is a bit like the capacitor circuit where we have a resistor, we can make it a lamp, and we have coil, and we put a voltage on it, DC voltage. What's going to happen is we're going to get a current flow. When you get, and the current's going to try and rise very rapidly. So when you get a current flow through a coil, it creates a magnetic field. Well, the current through any wire creates a magnetic field, but through a coil we get that sort of solenoid effect. We've got a strong magnetic field in the coil. Strong magnetic field in the coil gives you a strong flux. We now know from Faraday's law, or from the other ways I've taught you to think about this, that change in flux over change in time is going to give us a voltage in that coil. Now, the voltage is going to be produced by this EMF, which is going to be trying to oppose the change of flux. So if we've got a flux through this coil which is increasing, which it will be if the current's increasing, it's going to try and oppose that by creating a opposing voltage. So when the current's trying to increase, as soon as we turn that on, it's going to create a voltage in the coil like that. Now, each coil, depending on how it's made, how many turns it's got per meter, what its radius or what its area is, that's going to determine the actual self-inductance, which we've given the symbol L. I'll make another little video where I actually show you how to theoretically calculate self-inductance of a coil. All I wanted you to know from this video is what's going to happen with this. And remember the curves, and I think we already went through the equations or the formulas for the curves with the capacitor. They're very similar for the inductors, and I will do a little video on that. But remember that the voltage time curve was like that for a capacitor, and all you need to remember, all the other three curves were like this. All you need to remember is that for the inductor, this is the current time graph in the inductor. Okay, so the current tries to build up rapidly, but we get this opposing voltage, and so it takes a little while for the current in the coil to build up to its maximum value. At this stage, the current is steady, and it would be the same current that we'd expect from having that voltage, that resistance, and the small amount of normal resistance that's in that coil. And that's what that current will be. So that current would just be the voltage over the resistance in the circuit. But it can't immediately get to that point, because as the current tries to rise to that point, this little baby, this coil, produces its own voltage to oppose the flux change.